Hello, my name is Alissa S, and I teach mathematics at Loyola Marymount University in Los Angeles. I'm also the Associate Director of Diversity and Outreach for the Mathematical Sciences Research Institute located in Berkeley, California. I'm extremely grateful to the MAA for the opportunity to be here today and to talk with you about a very famous sequence of numbers called the Catalan numbers, after the 19th century Belgian mathematician Eugene Catalan. Let's start off by reminding ourselves of some other famous sequences of numbers that perhaps we've seen before. Of course, there's the counting numbers. 1, 2, 3, 4, and so on. We can also talk about the perfect squares. 1, 4, 9, 16, and so on. Of course, we get these by starting with the counting numbers and squaring them. We can also look at powers of 2. 1, 2, 4, 8, 16, and so on. And we get these by starting with the number 2 and raising it to various powers. So the first is 2 to the 0, then 2 to the first, 2 squared, 2 cubed, and so on. Finally, perhaps you've seen the Fibonacci numbers. 1, 1, 2, 3, 5, 8, and so on. Remember, we get the next number in that list by adding together the previous 2. Just like all of these examples, the Catalan numbers are an infinite list of numbers. Let's discover what they are. Suppose we're all at a large party, seated around round tables. And we'd all like to simultaneously introduce ourselves to someone else seated at our table. The only condition is that we don't want our handshakes to cross. If we think about this for a minute, that means that the number of people at our table needs to be even. Suppose we have 3 people at our table. While 2 are busy shaking hands, that third one is the odd one out. And this will be the case no matter what odd number of people we have. So again, the question that we'd like to answer is, in how many ways can we do this? In how many ways can an even number of people simultaneously shake hands so that our hands don't cross? Let's keep track of the number of ways on the board behind me. If we start off with just 2 people, well, that's kind of boring. 2 people only have one way that they can shake hands with one another. If now we have 4 people, well, let's think about this for a moment, remembering the condition that we're not allowed to let our handshakes cross. After a minute of thought, we'll realize that we only have 2 options. I can shake hands with the person on my right or the person on my left. I can't shake hands with the person diagonally across from me because when I do that, well, then the person to my left, their handshake will cross mine, and that's not allowed. So for 4 people, we have 2 ways. Finally, if we consider 6 people seated at our table, a bit of scribbling on a piece of paper and thought will reveal that we have 5 ways of doing this. Now that we've got the hang of this question, let's turn to another question. We'd like to draw pictures of mountain ranges, where we have the same number of upstrokes as downstrokes, and we have the condition that we're not allowed to go below the horizon. So what that means, for example, is that our very first move can't be a downstroke. These mountain ranges are named after the 19th, early 20th century German mathematician Walther von Dyck. They're called Dyck paths. And we'd like to know, in how many ways can we draw these Dyck paths? If we start by allowing ourselves 1 upstroke and 1 downstroke, well, that's pretty boring. We have a single mountain range that we can draw. If we allow ourselves to have 2 upstrokes and 2 downstrokes, if we think about this for a moment, because we're not allowed to go below the horizon, our first move can't be a downstroke, so our first move has to be an upstroke. We have 2 ways of doing this. We can alternate up, down, or our first 2 moves can be up, our second 2 can be down. Finally, if we allow ourselves 3 upstrokes and 3 downstrokes, a bit of scribbling on a piece of paper will reveal that we have 5 ways of drawing those mountain ranges. So we see that we're getting exactly the same numbers to answer the question about the number of mountain ranges as we did to answer the handshake question. It turns out that these numbers show up as the answers to many, many questions all throughout mathematics. They're called the Catalan numbers, again after the 19th century Belgian mathematician Eugene Catalan. These numbers are an infinite list, just like all of the examples that we talked about at the beginning. And after 5, they continue on with 14, then 42, then 132. We actually have a formula that describes what the Catalan numbers are. So for example, if I were interested in knowing what the 10th Catalan number is, I could use this formula to determine that. Looking at the formula, we see it involves factorial. So that exclamation point isn't expressing enthusiasm. It's giving us a way to form a product. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1. We start with the number, we multiply it by the counting numbers before it. So the 10th Catalan number would be 16,796. We get that by taking the number 10 and substituting it in for n in this formula. Now, since the answer to both of these questions that we asked are the Catalan numbers, what that suggests is that, well, these questions must be related to each other in some way. And in fact, they are. And let's see how they are. What we'll do is we'll start with one of our handshake tables, and we'll see how to recover from that one of our mountain ranges. In particular, we'll start with one of our 5 handshake tables amongst 6 people, and we'll come up with a way to obtain one of our mountain ranges where we allow ourselves to have 3 upstrokes and 3 downstrokes. Now, in order to do this, we're going to enlist the help of a very smart mathematical bug. She's going to start down at the 6 o'clock position of our handshake table, and she's going to make her way around the table counterclockwise. Now again, this bug is very smart, and when she encounters a handshake pair for the first time, she's going to shout out the word up, and that'll tell us to draw an upstroke in our mountain range. Now as she continues traversing the table, when she encounters the second person involved in a handshake, well, she'll shout out down. She's already passed that handshake pair before. That tells us to draw a downward stroke in our mountain range. Let's look at this particular handshake table. As our bug starts around, she encounters 2 people who are the first people involved in a handshake pair, so she shouts out up, up. But that third person that she encounters, they were shaking hands with the previous person that she just passed. So she's already seen this handshake pair before. She shouts out the word down. Let's give our bug a rest up at the 12 o'clock position while we think about the mountain range that we'll have drawn. So again, she shouted up, up, and then down. Now she's going to continue from the 12 o'clock position, going around the table. This first person that she encounters, well, they were shaking hands with the very first person that she passed. So she's seen this handshake pair before, she shouts out down. As she continues along the table, she'll shout out up, then down. So it's from this method that we're able to construct the mountain range associated to this handshake table. It turns out that this process is reversible. That is, we could start with one of our mountain ranges and recover one of our handshake tables. Mathematicians call such a reversible process a bijection. And it's because of the existence of this bijection that mathematicians would say that our 2 questions are the same. Now we've only had time to consider 2 questions whose answers are the Catalan numbers. And it turns out that there's many, many more. Richard Stanley, a professor of mathematics at MIT, has collected a list of over 200 questions whose answers are the Catalan numbers. They appear on his website. As a final remark, I'd like to point out that even though these numbers bear the name of Eugene Catalan, they were actually known to the 18th century Swiss mathematician Leonhard Euler. Euler is considered to be one of the most prolific of all mathematicians. He made contributions to areas as diverse as geometry and trigonometry, to calculus and number theory. Moreover, we recently have accounts that tell us that these numbers were known to Chinese mathematicians even before Euler. It was a pleasure to be with you today. Thank you very much.